Hello, welcome back to the course. So, last day we talked about super twisting algorithm and we covered the basic theory which proved the convergence of the super twisting algorithm. And but we did not look into so much in how we can work with the super twisting algorithm. So, when I will be setting the assignments, then you might face some difficulty in trying to fit that super twisting algorithm into the actual into deriving the control for the actual system using that algorithm. So I will try to walk you through how to do that using this presentation. So our intention of this presentation is to use the super twisting algorithm that we had learned last time and use it to derive a control action for a real physical system or the model of the real physical system that we are having with us. So we all have some model with us to work with, and we will be able to see how we can use the super twisting algorithm to design a control action for that particular model. So as you have seen, the super twisting algorithm looks like this. This is the form of the super twisting algorithm that we have proved convergence for, and these are the assumptions and the controller gains that we had for this form. So here we have the assumption that H and G both are unknown to us. However, they are bounded by this condition: H dot plus G dot mod of H dot plus mod of G dot U capital M is less than equals to C, and G is bounded by these two positive quantities. And this is also a relation that we had satisfied. So with all this, then we had shown that now if we set the controller gains in this manner, then this algorithm converges in finite time to S equals to S dot equals to 0. So now we'll see that what this is actually. This part is same as this part. We can write this in this way. So we simply plug in this U here. When we plug in this U, then this becomes this where U1 is minus alpha sin S, right? And this is also, this one can also be written in this manner. So this is simply another, you take another derivative S double dot you take, then you will get this thing, this form. So we are putting in both of this because in some of the systems we will use this form, some of the systems we will use this form. Now this is another form of the super twisting algorithm which we have seen in the last time presentation, and I have asked you to already the assignment is given. I have asked you to simulate the super twisting algorithm which appears in this form. This is the most simplest form of the super twisting algorithm, where we don't even have the uncertainty here, you see. However, we will introduce the uncertainty just in a few slides. So anyway, however, we have not proved the convergence of this form. We have proved the convergence of this form, right? So we need to see how this particular form and this particular form corresponds to each other. Now if you look closely, this form translates to this form when Hx is 0, Gx is 1 and U1 is new. As simple as that. So when you know that this is the these are the values of the quantities in this form which we have proved for convergence, then you can set the gain conditions of lambda and alpha for this particular form by knowing that hx is 0 in here, gx is 1 in here, and this u1 which is here is same as the new. So we don't have to do anything here, no change here. So what is coming here? So in the assumption side, you see hx being 0 means h dot is also 0, hx is a constant 0, gx is also a constant 1, so g dot is also 0 here. So that means we simply need to put c more than 0, c simply needs to be a positive number, nothing else. So in the if you see the gain conditions, km alpha greater than c, that means since km is already a positive number, alpha simply needs to be a positive number, that's all. Now if you see here, your gx is 1, so your km is less than 1, this k small m should be less than 1, k capital M should be greater than 1, that's all. So we are worried about k small m because that comes here in the controller gain conditions. So k small m must be less than 1, and you make it if you make it like, okay, so this is simply, this needs to be less than 1, but you also have this condition, this should be greater than 0, so don't make it negative, okay, because negative km will make you come with a negative alpha, which is not the case that we are considering. We have a positive km and positive alpha. And if you look here, then h is 0, g is 1, you have some bound um and whatever q, so whatever these values, these are greater than 0, so these assumptions are met already. So you have selected your alpha, so now you can select your lambda based on your value of alpha and your value of km and some q that you are choosing. C here is 0. So with this understanding, now you can simulate this particular dynamics by evaluating the controller gains or selecting the controller gains in this manner, okay. However, this is for without uncertainty, no dt is there, but the dt can be there and we will see that. But before that, we also look into this thing where we are considering the other way of representing the super twisting algorithm in S double dot form. So when we make it S double dot form, then what happens, we have this equation, and in this equation we have to know what g dot is, but since gx is already 1, g dot is 0 and h dot is also 0, okay. So this thing should be kept in mind. So this is also equivalent to this, and here h and g's values are like this, h dot and g dot both are 0, the same thing written in a different fashion. So here you see we have introduced the disturbance term dt here, and this sort of a form we are having, and how this form corresponds to this form. Here you see when you are doing S double dot here, then you are having a differentiation of this term which is coming here, and then a new dot which is giving alpha sin s plus dt, okay. So now if g is set as 1 and that's why g dot is 0, then what you will find out is that h dot becomes equals to dt. So h dot here is dt, so this dt is basically h dot. So you need to know the bound of this dt which is coming here, and this h is the integration of dt. So you do this function, whatever function is there, that should be integrable So the functions all are integrable in nature. So and you have to find out a bound of that function, and you set your accordingly, so that this quantity becomes more than this bound. So this is what happens when you have a disturbance added to it. So now if now I have asked you to simulate this particular function, this particular algorithm in this form. Sorry, I should use the pointer. So I have asked you to simulate this particular algorithm in this form with the dt here, and you will be choosing the dt as sine wave or square wave or sawtooth. So whatever you are choosing, you can have a integration done, and you see what is the, if this condition is getting met or not. So you have to choose your capital accordingly. You have to choose your capital accordingly. Okay. And now these conditions are also there, which you will be able to satisfy, because you know now that h dot is equals to gt. H dot is equals to gt, and this is 0 because g dot is 0. So what you need to have? You need to have c more than this bound of dt. So that will determine alpha, and that will determine lambda. So in this way your controller gains will change. Now we will see how we can do some implementation with this super twisting algorithm. So we will consider two cases where one is where the sliding variable is rd1 and another where the sliding variable is rd2, and you will see that the super twisting algorithm is suitable for, or I should say most suitable for relative degree 1 sliding variables. Now you see this example, then you will understand. So we have a general nonlinear system like this: ax plus bx u plus ft. We define a sliding variable sx which is relative degree 1. So then s dot will be like this, and this part will be non-zero. So u is coming, so we represent this as capital Hx, this as capital Gx, and some dt is coming. What is dt? dt is dou s dou x of ft. You see, we have not taken into consideration any matched or unmatched criteria on the disturbance. Okay. So now, so this is so now so this thing on the disturbance, that we can have even have unmatched disturbance in this case. So this is one benefit of super twisting algorithm, we can say. So now you see the next slide. If ax and bx are known, so suppose this ax and bx are known, what does that mean? This means that this hx and gx gets known. These are also known. So if hx and gx are known, then we can have the controller like this, obviously provided that gx is invertible, and of course gx will be invertible because this is non-zero everywhere in the domain that we are working in. So this is non-zero. If this was 0, then the relative degree would not have remained 1. Okay, so this is non-zero. So this is also non-zero, so we can have this sort of a controller proposed. So if we have the controller like this, then what happens? You see, this s dot takes the form like this. S dot will be equals to, so this is cancelling out, hx will cancel out, so minus lambda mod s to the power of half sin s plus nu plus dt is there, and nu dot is this. So this form is it is taking. So in this form, if you look back into the slides, you will see that S dot was having small hx plus small gx, all those things. So small hx will be equals to dt here. So only one uncertainty is there, which is dt. So small hx will be dt. So whatever assumptions we have set for small hx would be applicable for dt, and gx here would be 1. So whatever assumptions were taken for small hx should be applicable to dt, and this is one very important assumption that we had taken, which is h dot of mod of h dot was there in one of the assumptions. That means this mod of d dot needs to be known. What does this mean? This first of all means that d dot should exist and it should be bounded. So this means that this implies that ft, because dt is coming from ft, dt is this. So when you do a d dot, we will have to do a f dot. So ft needs to be differentiable. So this is what is meant by this. So this is one assumption on the disturbance that we are keeping. So what does this mean? This means that if you have a system, then in the system you can't put any uncertainty. The uncertainty must be at least one time differentiable for RD1 cases. So this is one constraint that we are putting on the uncertainty, which was not present in the classical sliding mode control case. There the uncertainty needed to be only bounded, not differentiable. It may not be differentiable, it just needed to be bounded. Here we are putting an additional condition of differentiability. However, in most practical cases, this uncertainty that comes in, this disturbance that comes in, is not very high frequency disturbance. So it is a low frequency one, and whenever you have a low frequency signal, that means it is having some smoothness associated with it, so it will be differentiable in nature. So normally practical uncertainties are differentiable in nature, so this is why this will work. So no problem with this assumption. We will see this case where A and B are unknown. So when both A and B are unknown, then hx and gx also becomes unknown. So when hx and gx becomes unknown, then you can't have that gx inverse hx plus lambda, those kind of thing you cannot have. So here you have to directly use this u equals to minus lambda s to the power of half mod s to the power of half sin s plus nu, where nu dot is like this. So this is the usual form that we know, that we have proved the convergence for. However, here we have to be careful what small hx and small gx has become. So small hx has become capital Hx plus dt. So you see s dot was, so in the expression which we proved for convergence, it was having s dot equals to small hx plus small gx u, and then you choose u like this. So here then small hx will be capital Hx plus dt and small gx will be capital Gx, and then the conditions that needs to be satisfied, the assumptions on small gx and small gx has to be satisfied by these entire quantities. So since h dot needs to be known, this implies that both ft and a, so what what is hx? Hx is coming from la sx and ft is coming from this dt. So both of these needs to be differentiable. Actually a does not need to be differentiable, because la sx is del x ax, del s del x ax. So a does not need to be differentiable, only ft needs to be differentiable. Okay, so this is extra thing I had added wrongly. Next we will see for RD2. In RD2 we cannot stop at S dot, because S dot will not contain the control input. That is the nature of RD2. There is a, by definition it is like that. So the LBSX will be equivalently 0. So then we have to go to S double dot. In S double dot we will have this form coming in, and this LBLASX, this Lie derivatives, this chain of Lie derivative will be non-zero. So then you can come in the second derivative of S. So this is, that's why it becomes RD2 in nature. So now your capital Hx is this and your capital Gx is this, and there is another D dot T which is coming here. So this format is, this form has come from the system. And what is this D dot? This D dot is this thing. This D dot is this thing. So you can verify this. And then what would be the control action? So here we have changed, we have put this equation in the top. So this is the equation that we are coming out with from the system, states and the sliding variable that we have defined, the RD2 sliding variable. So now our job is to choose such an U which will give us this form, because we have already proved this form. So in the form that we have proved, you will see that H dot becomes equals to D dot here. So there was a H dot plus G dot U. So H and then G into this, then minus alpha sin S. So G is 1, that's why G dot is 0, so that U term is not there, and D dot will be equals to H dot. So H and D will be same. That means this is same as this form, this form is same as this form. Okay, and now if your AX and BX are known, then you can fix the controller like this. You can choose your U like this, which will give you this particular form, and here you know your H dot and is equals to G dot is equals to D dot and Gx equals to 1. So what we have we can conclude here that D dot needs to be known. So D must be differentiable, but if you go back to the last slide, you will see that D dot equals to something into Ft. So Ft does not get differentiated. That means Ft, which is the actual uncertainty coming in the system, that does not need to be differentiable. Okay, so this is the case here. So that does not need to be differentiable. So for if you are working with relative degree 2 sliding variable, then the interesting thing is that the main uncertainty Ft may not be differentiable, but still it will work. However, if you are working with relative degree 1 sliding variable, then the main disturbance Ft needed to be differentiable at least once. So this is the difference. So we will not go into the case where Ax, Bx are unknown, because that will be a bit more complicated, and let us not go into that. So we will end the presentation here, and I will give you some assignments based on this knowledge what we have. Already one assignment has been given, which will need you to use some of the knowledge in the first few slides of this presentation, where we have two forms of super twisting algorithm, and we have to make a correspondence between both of these forms, because one of those forms we have proven, the other form we have not proven for convergence. So to choose the gain conditions of one of the form, we have to refer to the other form and find out the correspondence between the two. Similarly, after that, what the next assignment will be is whatever system you are working with in classical sliding mode control, that was having a relative degree 1 sliding variable. So you should go through the slide where we have designed the super twisting controller for the relative degree 1 sliding variable, and that is what you will do. Instead of designing a classical sliding mode control, you will replace that with a super twisting control. The advantage is that you will get a continuous control action, so there will be no chattering. However, you have to keep in mind that your disturbance and uncertainty that you are giving to the system must not be discontinuous in nature, must be differentiable. So you can check by giving a non-differentiable signal, which is a random number like that, and see what effect it gives to the system using a super twisting controller, and then you can see for smooth disturbances what effect it gives to the system. So this assignment I am going to formulate after I upload this lecture. Thank you.